In addition to this prompt photocurrent, which is due to the electron hole pairs that are generated by the photons in the depletion region, you can also have excess charge generated outside of the depletion region in the N part of the p-n junction and the p part of the p-n junction. And we can figure out the distribution of those excess charge carriers from the ambipolar transport equation. So for the ambipolar transport equation, we're going to make a couple of assumptions that will simplify the equation. So we will assume that the electric field goes to 0 outside of the depletion region. And we'll also assume that this photodiode is in steady state, so the excess carrier concentration is not changing with respect to time. So the ambipolar transport equation will reduce. This is for electrons in the p side of the semiconductor. The equation will reduce to this form. And that capital G sub L is the generation rate due to the photons. So we can solve this equation by setting up the appropriate boundary equations. We've done something like this before when we've looked at ambipolar transport to figure out the excess charge carrier concentration. So this is a similar kind of solution to this differential equation. And the end result will be these two equations for electron concentration on the p side of the junction and hole concentration on the n side of the junction. This figure from your textbook shows those minority carrier concentrations, excess minority carrier concentrations on each side of the p-n junction. I'd like to point out that this is actually should have this notation. So this is the excess holes in the inside of the junction. Anyway, there is you can see that there's a higher concentration of these excess charge carriers away from the depletion region. It decreases as you get closer to the edge of the depletion region. So this gradient will result in diffusion of holes, these excess minority carrier holes from the inside or towards the p side of the junction. That corresponds to a current, this J sub P1. And this is one component of something called the delayed photocurrent. Similar on the p side of the junction, so we're looking at excess minority electrons in the p side of the junction. There is a gradient, so electrons are going to want to diffuse towards the left. The current therefore should be in the opposite direction, and there is a delayed photocurrent due to that electron diffusion, J sub N1. Let's quantify these two delayed photocurrents, or these two components of the delayed photocurrent. So J sub N1 is going to be the electronic charge times the diffusion coefficient times the differential of that excess electron concentration in the p side, and we'll evaluate that at x is equal to 0. That comes out to this expression by substituting in the equation for that excess electron concentration that we wrote previously. And if you rearrange some terms, we can write it in this form. And you would solve a similar differential equation to get the second component of the delayed photocurrent due to the holes and that looks like this. From these two equations, we can see that the second term in each one of these equations, these are part of the ideal saturation current density, and the first term in each of these two equations is proportional to the generation rate of the charge carriers due to the light shining on the photodiode. So these first two terms are going to become part of the photocurrent density. So then the total photocurrent density in our photodiode is going to be J sub L. That will consist of these the prompt photocurrent and the two components of the delayed photocurrent. So this is E time electronic charge from the generation rate times the depletion region width the delayed photocurrent is electronic charge times the generation rate times diffusion length of electrons, and electronic charge times generation rate times the diffusion length of holes. Also, let's go back to the direction of this photocurrent. So here's our PN junction. We are reverse biasing this. So if you were going to draw a current around this loop, right? This is the current around the loop. So in the dark, we just have a reverse biased PN junction. I expect that the value of that current is going to be very small. Now when we start shining light on our photodiode, we get an additional current here due to the carriers generated in the PN junction. And so that means that the current around the loop has increased. And so that's going to be the electrical signal that you're looking for in this type of photodetector. If the current through this photodiode is going to increase in proportion to the amount of light that's shining on it.